Okay. Good morning and sorry for being late. I just wanted to check if everything is fine so far. We already had some 20 hours. So if you have any problem with this subject, like, I don't know, difficulties in understanding or suggestions to give to me, or maybe you may have problem in figuring out the structure of the topic that we are dealing with. Any doubt that you may have, please let me know. Okay? Do you have any urgent question or suggestion? Urgent, I mean something that you want to discuss now? Everything is fine. Okay? And your experience with the R, personal computer, everything is fine so far? Okay. Today I'm not using, I took the cable and the controller just to make sure that I have everything, but I'm using the blackboard today. Okay, I put the camera there. And yesterday I was told by Emanuele that you succeeded in modeling the rainfall runoff relationship with the linear reservoir model by using a code that you more or less wrote by your own, and I was told that at the end of the lecture you did the calibration of the parameter. And probably you may have noticed that if you made a comparison between the observed data that Emanuele should have passed to you, and simulated data, you may have seen that they don't match really well. First of all, let me say that I'm not really sure, I tried to clarify yesterday with Emanuele, if he used the same data that I passed to you before, because I gave you rainfall and evapotranspiration data. I refer to the same catchment, but maybe that he chose a different observation period. Anyway, it's not a problem. Yesterday you used the data that Emanuele passed to you, took this data, and it's not really, it doesn't matter what is the observation period that he referred to. But in any case, whatever the observation period, for sure you have seen that the simulation is not really good, they don't really match well. The reason why they don't really match well can be manifold, but for sure one candidate reason, one plausible reason is that the model is linear and it's a very simple model, which counts only one parameter. So this is something that you have to get used to see. What is a simple model? What should you look at in order to understand whether a model is simple or not? And of course, there are some personal considerations that you may make, like for instance, you may consider that a model that you were able to apply in a couple of hours, it's necessarily simple, because complex model may require 1 week to be set up. And this is one first consideration. A second, more quantitative assessment that you may make is related, as I said, to the number of parameters. Because if a model becomes more flexible, it implies, flexible means that it's more capable of adapting itself to the process we are trying to simulate. So if the model becomes more flexible, more capable of adapting itself to the process, necessarily it must have more parameters. So if the model has, let's suppose, 0 parameters, it's never our case, the model is fixed, you can't adapt it to the specific catchment, to the specific process, you can't account for any uncertainty. If you increase the number of parameters, the model becomes more flexible. You can think, for instance, at the linear regression and the polynomial regression. The polynomial regression is more flexible, but implies a larger number of parameters. So the linear reservoir is a model that counts 1 parameter, and therefore cannot be very flexible. This is the main reason why the model didn't provide a very good simulation. I'm not sure if you computed the mass efficiency of the simulation, and it would be a useful exercise. You may see that probably it ranges between 0.5 and 0.6, which means that it's not very good, as I mentioned to you on Tuesday. So basically, there is an advantage actually in using a simpler model. In using a model that is not much flexible, there is an advantage. And the advantage is called robustness. We say that the model is more robust. What does it mean, robustness? It means that the model may be not much precise, but on the other hand, it doesn't fail much. So it's not much precise, but on the other hand, it doesn't fail much. Which is, I mean, a good behavior. Because you are certainly concerned to get a good fit with the model. But you are also concerned to make sure that you don't make big mistakes. So when we say a simple model is more robust, we mean that the model probably is not much precise, but on the other hand we have the advantage that the model doesn't make big mistakes. It's, you may easily understand by intuition that if you have several parameters, the model becomes more flexible, but when you simulate, the presence of so many parameters gives rise to a variety of different solutions. So if you have only one parameter, you change this parameter and you get a different solution, a different simulation. But the spectrum of the possible simulation is not much wider. It's not wide, it's not much wide, because you have only one parameter that you're changing. If you have 10 parameters and you change all of them, you get several different combinations, you get a wider spectrum of possible simulation, including those that may be really wrong. And therefore, simplicity is sometimes preferred for the sake of robustness. I'm talking now of model fitting, model robustness, which means model performances. And so far, we didn't speak about checking the model performances. We just spoke about calibration. We know how to find the values, the optimal values for model parameters. Now let's try to discuss about checking model performances. What is called, I already anticipated this term to you, what is called model validation. We can use some synonyms for model validation. In hydrology, by far, this is the term that is most used, but you can speak of model verification, for instance, or you can say that you are checking the model performances. There is one important concept that I would like to introduce to you. You may say, I already made yesterday a check of my model performances because I compared the simulated data with the observed ones. And I mentioned to you that you may compute the Nash efficiency, which means checking the model performances. So you may say, I already did it. Actually, this is not true, because what you can do if you perform a calibration and after calibration compare observed and simulated data, what you are doing is checking how the model performed in calibration, which means that you instructed the model to reproduce well a set of data, you forced the model to reproduce well then, the model learned from this data and adapted. This is not the same situation that you experience if you go on the field and you apply the model in practice. Because when you estimate as an engineer a design variable, you don't know the true value. Because if you knew the true value, you didn't know, you didn't need a model. So basically, when you apply these models, this purpose is to simulate data that you don't know. So calibration is just a step to get the model useful, but it doesn't reproduce what the model is meant to do in practice. It's just a learning exercise. The model learns in order to get ready to be applied. In calibration, you are trying to reproduce data that you already know. So this is not what the model is supposed to do. It's just a learning process. It's just a step to get the model ready to work. But actually, the model is conceived to reproduce variables that you don't know. I said at the beginning, you may remember what is our general purpose here. Our general purpose is to reproduce river flow data because we don't have them. Or, if you have them, we have only a few. And therefore, it's implicit in this definition that the model is meant to reproduce data that we don't know. Calibration is a step, again, to get the model ready. So in order to get the model ready, I get some observed data, if I have them, and I already told you that there are techniques which we don't study to calibrate the model if we don't have data. In our case, we're supposed to have some data, and we get the model ready. But, as I said, we force the model to reproduce this data. And now, the model is ready to be used in practice. And what we want to check is the actual performance of the model in practice. So basically, we have to check the model to reproduce data that we don't know, or we assume to not know. This is validation. Validation is, I repeat the definition later. Validation means checking model performances in a reproducing data that were not used in calibration. I repeat, validation means checking model performances in reproducing data that were not used in calibration. Let me make an example. Let's suppose that you have some observed data. And let's indicate them with the symbol Qt against time, an hydrograph. So you have this hydrograph here. And you have this data. And you want to apply a model. So basically you want to, these are observed. And now you want to apply a model to reproduce this data. Let me see the color of this chocolate. Perfect. Now, if we use a model, we obtain another hydrograph. So let's suppose now that we split the data into pieces. So let me draw a straight line here. And let's suppose that we use this chunk of data to perform a calibration. And then we get some hydrographs here, an hydrograph here. The reproduction may be good, maybe not so good. This is what you obtained yesterday. So you reproduce data that were used, that are being used to calibrate the model. And please note, in this case, you are forcing the model to pass through this data. You are forcing the model to reproduce this data well. Why is that? Because you are computing an objective function that minimizes the errors. So you are telling the model, find the best solution, your best solution, to reproduce well this data. So this is a kind of favorable situation, because you know the data. Now, we get to this stage, and from here we get the parameters. We get theta. Look, these data were not used in calibration. So now what could we do? We could try to run the model to reproduce the data that were not used in calibration. I can assume that these data are unknown. I use them only to get a comparison with the model simulation, but I don't use them as a constraint. I don't push the model to fit this data. I just let the model go with the calibrated theta. Okay? And then here, what would you expect? Would you expect better performances or worse performances in reproducing this data? I would say that I'm expecting worse performances because these are new data. The model was not trained, was not instructed to reproduce them. So what I'm expecting is, if I go on with this hydrograph, something that is less accurate. And then one can compute an objective function like the Nash efficiency in calibration and validation. Let me write validation here. You can compute the Nash efficiency in calibration and validation, and you would notice that the Nash efficiency typically decreases. This is validation. You take a piece of data that you don't use in calibration, and you run the calibrated model to reproduce them. This is validation. And I said that the performances decrease. Actually, sometimes it may happen by chance that the performances increase. By chance, because we have uncertainty in here. In this modeling exercise, we have uncertainty. Uncertainty means several possible chances. So you may also get, if you are lucky, a chance where the model performs better in validation than in calibration. But on average, you would get worse performances in validation with respect to calibration. So basically, I hope it's clear what the difference. Once that you get a calibrated model, you are not sure that the model performs well when we go to apply it. Because you didn't check, you didn't emulate a real-world application. Calibration is not an emulation of a real-world application. Calibration means just pushing the model to reproduce this data. If you want to check how the model performs in a real-world application, you have to do a validation, which is a real emulation, because you assume that these data are not known. You just use them afterwards, after running the model, to check how it works. Is this clear? Okay, and there is a problem here, a disadvantage. The disadvantage is, first of all, before saying the disadvantage, let me make an observation, a comment. Validation is more and more important the more complicated the model is. Because I told you that the more complicated model is less robust, and if you are doubt on the robustness of the model, it means that you need to validate it. You have more reasons to validate it. Yeah, please.
I have a doubt about the order of magnitude. What is the time that we should run the validation in order to think it can...
Yes, let me go on. Okay, I was just saying that. I was after this comment that I made. I was just saying that you see a problem here, an open question, and the open question is the question that she asked. Basically, the open question is related to choosing the length of observation period and splitting it in calibration and validation. How long should be the calibration period? How long should be the validation period? First of all, let me say that we usually have a few data only. And therefore, this is a relevant question, because if you had plenty of data, you wouldn't need to apply the model, because our problem is that we don't have a lot of data. And therefore, this question on how long should be the calibration period, how long should be the validation period is a very relevant one. Because ideally, we want to maximize the length of the observation period that we used for calibration. Ideally, we want to maximize it. Because given that we have a few data only, given that there is uncertainty, ideally we want to estimate the parameters by using all the available information. We don't want to discard some information. And therefore, one would be tempted to either not to make validation at all, or to reserve to validation a few data only. And therefore, this is contrasting the necessity of validating the model. So, what should we do? First of all, if you perform a validation, whatever is the length of the calibration and validation period, once that you check the model performances in validation, what you should do is to recalibrate the model by using all the data. Because at the end of the story, when you go on the field, when you estimate a design variable, you should use all the information that you have. You shouldn't discard part of the information because you wanted to validate the model. So you make a calibration, you validate the model. If you are happy, you recalibrate the model with all data, and you finally use it. Of course, you may say that the model that you are finally using is not the model that you validated, because you recalibrated it. But, on the other hand, you can check what happens. So let's suppose that you perform calibration and validation, you are happy. And then you recalibrate the model before the application. Let's suppose that you get completely different parameters. Then you get suspicious. You say, oh, something is wrong here. And then you take additional care before applying the model. On the other hand, if you get very similar parameters, it means that you are along the right way, because there is not much uncertainty. You are concerned when you change the calibration period and the model changes completely, then you get concerned. But if you see that if you change the calibration period and the model is keeping its behavior, then that's fine. And let me say that you could, if you split the observed data into pieces, you could also invert the two periods. You perform a calibration and validation by using first period for calibration, second period for validation, and then you invert. You use the second period for calibration and the first period for validation. This is another way to check if the model behaviors remain, let me say, constant. It's another way to check if the model is robust. And keep in mind that in hydrology, you must be a little of an artist. Depending on the case study, you have to gain a feeling, I already explained this to you, and you have to devise means, additional means for checking what you are doing. You really have in hydrology and in water resources management to develop ideas. It's not like designing a beam. Everything is defined with rigor, and because there is reduced uncertainty when you design a beam. You compute the forces and the forcings on the beam, and then you have a rigorous theory to estimate it. When you estimate water availability, or you estimate the peak flow, the theory is not so rigorous, and you have to be, as I said, like an artist. You have to try to gain an understanding of what's going on, and refine your approach, depending also on your feeling. Now, going back to our problem, I said that at the end of the story, you need to calibrate the model by using all the data, and in order to perform calibration and validation, usually what we say is split the data in two pieces. This is what we say usually. And keep in mind that when you check model performances, you have to check its behavior in reproducing the process that you are interested in. So if you want to simulate a drought period lasts during summer, 3 months. It means that if you want to perform a validation, you have at least to reproduce the whole process, 3 months, at least once. If you reproduce only 1 month, it's not a good indication. Conversely, if you are interested in reproducing the peak flow lasts from a few hours to a few days. So the validation could be extended only to an high flow period. So validation could last for 1 day, for instance, because you are interested in reproducing the peak. It's better if you check more events, if you validate the model over several events, but of course, the period of time in which you are interested in checking the model performances is shorter with respect to the situation in which you want a simulated drought period. So basically, what is the optimal length of the validation period? To reply to your question, it depends on your application, and in this case as well, it doesn't exist a rigorous rule. What I would say is look at your data, look at what is possible to do, consider your application, and my suggestion is you need to check how the model performs in reproducing the situation you are interested to as many times as possible. I mean, if you have just 1 year, you check only one summer. But if you have 10 years of data, what I would suggest is to make this check along 5 years, for instance. And there is another thing that you could do. Let me suppose, and this is an important concept, because you know, hydrologists were concerned by these problems, were concerned by the need to perform calibration, but on the other hand, the need to make it very efficient, because you know, you have a few data only. And therefore, someone had this idea, which is a brilliant idea. Let's suppose that you have this hydrograph, Q, that lasts for 10 years. So let me put the years here, time in years. And years from 0 to 1, 2, 3. I limit myself to 3 years. And let's suppose that you have an hydrograph here. No? So someone had this idea, and someone who was interested in reproducing 1 year of data, let's say one drought period, someone had this idea, okay, given that the minimum length of the period, the minimum period length that I want to reproduce is 1 year, someone had this idea, let me take the first 2 years for calibration, and let me use the brown chalk for the calibration, and then the third year for validation. Okay, this is quite obvious. Now, let me rotate the year that I use for validation. So another possibility could be to make calibration in the first year, and in the third one, and then validation in the second. And then there is one more combination, which is first year validation, second and third year calibration. So the idea was to rotate the validation period by checking all the possible combinations. This is called, this is an important concept, jack, knife, calibration. Validation. Instead, this one, the traditional one, is called split sample validation. Jackknife is a brilliant idea. So you can perform several validations. I think it's indeed a good idea. Sorry, say again.
Can you please repeat the jackknife theory?
Yes, no problem. I mean, my premise was to identify the minimum length of the validation period. And I said, let's suppose that it's 1 year. It could be 1 day in some situations, but let's say that it's 1 year. Now, if you have an observation period of 3 years, and your minimum validation period is 1 year. This means that you can check in validation your model 3 times. So the first solution could be to use for validation the last year. The second solution, which I reported here, is to use in validation the middle year. And the third one, which I didn't depict here because I didn't have room, is to use the first year. And of course, you keep for calibration the other years. It's clear now? So, more or less. So, there is one doubt that you may have. You could say, how can I perform calibration on 2 separated periods? So, in this second case, you may ask me, how can I calibrate my model on the first and third year? Because yesterday you learned how to calibrate the model on a continuous period, not on pieces. So you may say, how can I calibrate the model by using pieces of data? Actually, this is very simple because you have, in automatic calibration, an objective function which we assume to compute over the whole set of data. So basically, let me write an objective function here, like least squares that I guess you used yesterday. Least squares, you can write it in this way. So, I don't remember the symbol that we used. Let me call it L theta. I hope it's the same that we used on Tuesday, but the symbol doesn't matter. Is given by summation from I equal 1 to n, where n we assumed was the total number of data that we have available, and we said that the summation is extended to qt minus q at t squared. Okay, this is the least square objective function. In my slides I used x because I used the generic variable, but again, symbols that don't matter. So basically, this is our least square objective function, and we assumed, I say again, that it was extended over the whole set of data. Now, you could write another objective function, L1 theta, which is equal to the summation extended from I equal 1 to n, to 10 of qt minus q at t squared. So I'm not extending the summation up to n, only to the first 10 data. I use 10, but could be 365, whatever you decide, plus the same summation extended from I equal, let's say, 20 to 30 of, again, the same quantity squared. Okay, I'm not writing anything here because I ran out of room in the blackboard, but it's the same summation, the same argument of the summation. Basically, you see that you can easily split a total summation into some pieces. It's just the computation of the objective function that changes. You don't have to rerun the model. You have to rerun the model because you have to re-perform a calibration, but you don't have to modify the model. It's just another run, and the computation of the objective function only changes. So you see that it's very easy to isolate pieces of data. You are just discarding the data between 10 and 20. These data are not used, so they can be used for validation. So it's very easy. And as I said, this idea of the jackknife validation was indeed a brilliant idea because it's very simple. Keep in mind that very brilliant ideas are not necessarily those that lead to complicated methods. The most brilliant ideas are those which make use of simple solution for gaining an advance. This is great. I mean, this idea of the jackknife validation came about 20 years ago, and indeed it's a great idea. You may say, why just 20 days ago and not 50 years ago? And the reply is computers. All these issues, all these procedures became possible after the 19th, so 25 years ago. And it's amazing how the introduction in our everyday life of the computers changed completely. It changed our life, basically, like probably the television did in the 50s of the past century. But our professional also life changed radically. And it's amazing also to think how the internet and the web changed our life. We don't realize it, because of course, when you improve for the better, you don't realize. And indeed, the internet gave an improvement for the better. But it's, if you think that the people started to surf the web 20 years ago, it's amazing. Try to think of what your activity would be now without a PC and without the web. Try to think of how your life would be, or without the cellular phone that people started. I started to use my cellular phone in '98, so less than 20 years ago. So try to think of our lives, how they would be, how we would behave without the PC, without the cellular phone, and without the web. And it was just 20 years ago. It's amazing. But as I said, you don't notice the improvements when they are for the better. And so basically this idea that was very simple indeed was conceived just 20 years ago and not before than that, because before than that, calibration and validation were done in a completely different way. Okay, so I think that for validation I can stop here. And let me say that there is an extended theory, an extended literature on calibration and validation. These are considered to be in hydrology and water resources management